Hey, hello students. I'm setting up this support session for assignment 1. So I will cover question 1 and 2 in this session, which you can use for reference. If you have any questions on question 3 on KNN, I will try and post a separate video for that, or just email me with questions that you do have on that, even on question 1 and 2. Okay, so anything about assignment 1, feel free to contact me, okay, via email. So yeah, I'm recording this, so I'm gonna make it available. Let me share my screen and I'll talk you through the content of assignment 1 and what's expected. Okay. All right, so let's go to assignment 1, and well, I'm just going to check again if I'm unmuted, recording and sharing. I think we are good to go. All right, let me get back there. Okay, so on the left, question 1 is very theory-based, and I don't think it's anything too complicated or analysis intensive. It's just definitions and understanding terminology. So obviously, I'm not going to give you the answers for this, but I'm going to give you a guideline of how to go about answering these questions. So for question 1, it says describe nominal, ordinal, interval, and ratio scales with examples, right? And explain their scale type, impacts, and statistical methods. So because there's different variable types, the question mark allocation is 10 marks. So what you're expected to do for each of them. So for instance, for ordinal, for nominal, interval, etc. What you want to address is what is the definition. Okay, so what is the definition? And provide an example. So you got definition, then you got example. Okay, you have to think of a real world example that can explain it. And then characteristics, is there a ranking to it, for instance? Okay. And how do statistical measures like mean or mode make sense for these types of variables? So you'd have to answer it for nominal, for ordinal, interval, and ratio scales, right? So how do statistical measures get impacted? So how do these affect statistical measures? I'm just going to put stat measures. All right. So another point is, how does scale type affect statistical methods? Is only one? Oh, sorry. Let's look at central measures, right? You got the average, you got the median, you got the mode. So sometimes you may have a variable that only has categories. So you can't really compute the mean unless you replace those categories with numbers. But if you kept it as categories, then which of those central measures would be valid? Would the mean only be valid, would the median, or would the mode only be valid? Okay, so think when you're answering them, think of examples and to kind of guide you how to answer them. All right, so look at that as your guideline. Okay, so that's question 1.1. So let me clear this. Cool. All right. So for 1.2, it's define and contrast training error versus test error. You can lay it out like that. So you'd have your train error, or the train error here, and you got your test error. All right. And the points you basically want to cover for each of them is, what is the definition, purpose, and the typical trend. What do we mean by typical trend? Well, let me give you an example. Let's say we were talking about a specific type of machine learning model, like XGBoost. right? So for XGBoost, the typical trend of this model or characteristic is that it tends to overfit. Okay, that's what we mean by typical trend. So you need to apply the same kind of approach when you're explaining train error and test error. Okay. And you can always add more. I only put definition purpose typical trend. That's a minimum. You can definitely add, and I do encourage you to add more rows to that. Okay, more points to cover. Okay. So let's move on to question 1.3. Let me erase this. How do GAMs enhance flexibility over linear regression models? So GAMS hasn't been covered yet. I know we still, even according to the schedule, GAMS is only going to be covered on Tuesday. So it's very close to the due date for the assignment, but it will be covered. So you can wait for me to cover that and do your assignment, but this is a very high level question. You can just do a quick research on it. You don't have to get technical and explain the math. You just want to cover what exactly does GAMS do differently to GLMs that enable it to handle non-linear data. All right, so there's just a few characteristics you want to talk about there. Obviously, I can't give you the answers, but do some reading up on that. It's pretty easy, but I will cover that this week. All right, so that's 1.3. Now for 1.4, explain how the bias variance trade-off impacts model complexity. All right, so yeah, you can cover a lot of points. So you can lay it out with bias here, and then you got variance here, and you can have them side to side so you can contrast them when you cover all the different points. Points you want to cover for each of them is what are they? Okay. How do they interact? Interaction. What do they tell us about the model? Okay, by using those measures, what can you determine about basically model performance? All right, so what do they tell us about the model? All right. Another point is, what does the high and low value mean? Okay, how do you interpret that for each of them? So what does a high and low value mean for each of them? Fourth point, how can they be used to determine underfitting or overfitting? Determine underfitting or overfitting. And you can cover more points. I just gave you can use these at the minimum, but please, the more the better. Okay, so even if you get some of them wrong, and if you got extra points, you can cover up with that. Okay, they can make up for the points that you got wrong. So put more points than less. All right. So that's question 1.4. Let's move on to the last question for 1.5. Here, this. All right. Question 1.5 is Lasso and Ridge use different types of penalties to control model complexity. So explain how the penalty used in Lasso affects the coefficients differently from the penalty used in Ridge. And then also describe elastic net, okay, and how it combines these penalties. So I'll lay it out like before, with lasso in one column and ridge in another column. Okay, and the point you want to cover for each of them is what are they used for? How do they go about doing it? What are the properties of each of them? And like before, when you were talking about the bias and variance, here, what do the large values mean? The point, are they shortfalls, disadvantages and advantages? Slash advantages. And then lastly, for elastic net, so these points will pertain to this table, and then the last point, talk about elastic net. How does it combine these two? All right, so give a brief overview of elastic net. All right. And that's pretty much question one, just to give you some sort of direction of how to go about answering it. Yeah, any questions on that, feel free to contact me. So let's move on to question 2. Now we will approach this with data. Okay, so you're going to use Excel and you just follow the instructions on how to answer this question. But I'll talk you through a similar problem. Obviously, I'm going to use different data and show you kind of how to go about answering this. So I'm going to close this and share my Excel. Oops. All right. Okay, I think it should be fine. So, okay, so in my data set, what my dependent variable is, or the target variable, is the sale price of a house. And the variables that I'm using to predict them is the size of the house in meters squares and the distance from the city center. Okay, so these are your x variables, x1, x2, or you can call them the other way. It doesn't really matter. But this is your y variable. This is the variable you're trying to predict. Okay, so from here, what you want to look at is first let's look at the correlation, right? And the Pearson's correlation between sales price and maybe just one of these x variables. So say house size. If I wanted to know how strongly they're correlated, all I need to use the Excel function correlate and then choose the data that I want. So I'm looking at the correlation between house size and my y variable sales price. So if I work that out, I got a value of 0.98. It's almost 0.99. So you generally want this correlation to be high as possible, as close to 1 or -1, because it means it's very strongly correlated, and you want that relation because we're using house size to predict sales price. If they weren't correlated, it wouldn't be a strong predictor. So this is the value you want to be high. Okay, and how do you interpret that? Well, that is a very strong positive correlation. Okay, the positive just says as your house size increases, the sales price increases, and that's kind of what you would expect, right, in the real world. Okay, the bigger the house, generally the higher the price. And here, sorry, you've got you can do a scatter plot for it if you want, just to see how it is visually. And what you also want to look at is maybe multicollinearity. Now, multicollinearity is pretty much the same thing we did with the y and the x variable, but instead now we're going to look at the x variables amongst themselves. So in other words, I'm looking at the correlation between the x values. So no y included. I just want to see how strongly correlated these x variables are. And here you want the multicollinearity to be as small as possible. You don't want your x variables to be strongly correlated. And the reason being is if they are, then there's actually no need to include both of them because one is pretty much as good as replacing the other. So you want it to be as low as possible. And in this example, you can see that the correlation is very high. So this is a strong multicollinearity value. You don't want this, okay? This is not ideal. And that's how you can check for multicollinearity, right? If you just got two predictors, it's very easy to just check it. All right. Yeah, so that's the correlation coefficient, how you could use it to check the correlation between your predictors of your x variables and your y variable, as well as checking for multicollinearity between the predictors themselves. Okay. Now, let's conduct a multivariable linear regression fit. Okay, so to do that, you would use the data tab, and you're going to have to use the data analysis tool. So you could highlight everything or just click the data analysis function. There's regression. Okay, click OK, and then it tells you to select your y variable. To select your y variable, all you could do is highlight the column that your y variable is on. Okay, and you do the same thing for your x variable. So the x variables, you're going to highlight all of your x variables. I'm highlighting the headers because there is a option that says, does this include labels? Or in other words, the headers, and you would click that. Okay, I generally like to put it in a new worksheet, but it's up to you. And then I would include residuals, residual plots, include standardized residuals. Normal probability plots is also worth including. Yeah, I've got everything. Okay, and you hit OK. I'm not going to do it because I already got it done already. Okay, you can put confidence level as well. You can click it pretty much everything if you want, obviously, other than the output options. Here, you got to select one. And if I click OK and run, you're going to get output like this. Let me just hide this. All right, let's talk about how we can make sense of this. All right, so let's start off on the top. You got your R square and your adjusted R square. These values you would look to determine how good a fit, or basically how good the x variables are predicting your y variable. You want this value as high as possible, okay, as close to 1 as possible. The higher it is, and what it's saying is that for this example, 98% of your variation of sales price in houses can be explained by your x variables. In other words, by your house size and your distance from the city center. Okay, so okay, so after you've got this output from running the regression function, you're going to get this table here. So let's look at our residual plots that we got when you click that option. Right, so for instance, here it is for house size, your x1, and this it is for your distance from the city center. A bit closer here, make it easy to see. All right, here are all your coefficients for each of them. This is for your intercept. I'm highlighting this in yellow because I'm just going to draw your attention in explaining that. So you'll notice that this is a negative value. All right. So what that means is that your y value and this variable move in the opposite direction. So the further away from the city center you are, okay, then the more your sales price of the house is going to decrease, right? So the closer you are to the city center, the higher the house price. Okay, so the smaller this x2 value, the higher your sales price. All right, so that's how you kind of interpret the sign. But let's look at the value and how do we interpret that. So because we got a value of 8149, so roughly 8150, what we're saying is that if you move a kilometer away from the city center, and I say kilometer because this is in kilometers. If you look at this variable, the unit is kilometers. So if you move a kilometer away from the city center, then that decreases the sales price by this value here. And the reason why I've got 8150, 8.15 million is because the units for sales, if you look at our data, it's in thousands. Okay, so even if it's 8150, you add 3 zeros, and that is the value that you're actually changing your y variable by. Okay. So here you'll get your residual outputs. Let's see here what you want to focus on. You also want to write out the equation for this line. Okay, so using these values, what is the equation? So let me open, give me a second, I'd rather do this on my whiteboard. Okay, so if I'll write out the values to show you how we write out the equation. Okay, so for x, our intercept, what we had was, so our intercept was minus 7094 3.88. Okay, that's what we had for our intercept. For x1, or house size, this is our x1. It was 1105.44. And then for distance from center, which is x2, that was minus 8149.57. And so how we would write this equation on, you simply just estimated sale price or in other words y hat is equal to minus 70943.88 plus the next value, which is this for x1, 115.44, x1 minus, the reason why I'm writing minus is because the next one, it's a minus sign. So it'll be minus, I'm just going to write it in the next line, 8149.57 x2. That's your equation. Okay, from our table. Okay, and you can use this equation to make predictions. So if you have a house with a certain size, you'll plug that in here for x1, and the distance from the center will be fed into here, and you get your estimated sales price. Okay, so that's our equation, and let's look at our residual plots. Okay, so this is your output. So one thing that I'm going to plot first is I'm going to plot the residuals. So yeah, this is your residual column and the y-axis, and I'm going to plot my predicted sales price on the x-axis. And this is the scatter plot I will get. Now, what you're looking for here is you're looking for a random scatter around 0, and you are getting that. Now, why are you looking for that? Because then that indicates good linear fit. Okay, you don't want it clumped up, and you don't want these dots to be following some sort of trend, like an upward line or downward line, or be cluttered together. And it does look like a random scatter here. Okay, so that indicates a good linear fit. All right. Another takeaway from this is you're looking for across the observations, you're looking for a constant variance. So in other words, you're looking for homoscedasticity, right? That's something you want. If the variance is changing over the observations, then generally the observations are time, but in this case it isn't. It's just each house, all right? You want the spread to also be random and not cluttered together, right? There's a good spread of these residuals, and that indicates homoscedasticity, right? Hopefully I pronounced that correctly. So that's the two takeaway points that you can get from looking at this graph. The other graph of the residuals is by plotting the observation number, right? 1, 2, 3, all the way to the last observation on your x-axis, and then plotting the residuals on the y-axis. And if you do that, you'll get this plot. Yeah. I know I had it somewhere. There we go. That's it. You'll get this plot. And here, you're looking for the same thing. You're looking for random scatter of these points. Now, what can you take away from this? Here, it's signs of non-independence. Why? Because you're not seeing any trend here. Okay, you're not seeing any cycle where your points are following some sort of wave-like structure or upward line or downward line. Okay, if you see it spaced out well and pretty much a random scatter, then that's an indication of non-independence. All right. So first plot, you can use it to check for non-linearity, okay, and homoscedasticity. And then the second one, you can use that to visualize for any signs of non-independence. All right. Those are your takeaway points from these plots. Okay. So I used this example of my data. Obviously, I couldn't use the assignment data, but the approach is the same, right? This is generally how you would analyze your data with just simply two x variables. I think I'm going to stop here. Yeah, if there's any questions about what I've covered, please let me know. Yeah, and I'll try and put a session up together for KNN. But if you do have any questions on that, please, yeah, drop me a note, and I'll go over that as well. Okay, thank you.